So we'll start with the definition of the decimal representation of an integer. So if n is a whole number with n plus 1 digits, probably we want to consider the positive whole number, although it can, let's stick to positive whole number for now. So it's possible to write n as follows. You can write it as, if it has exactly n digits, then you can write it out in this form, right? So for example, when you write it out in this form, we call this representation the decimal representation, or writing integers to the base 10. They can also be written to other bases, but today we'll only do base 10. So as an example to illustrate this, if you have this integer with only 4 digits, remember it's supposed to have n plus 1 digits. So this should be 3 plus 1 in our case. For this example, it has 3 plus 1 digits, which is equal to 4. So you can write it out as 2 times 10 raised to 3 plus 1 times 10 raised to 2 plus 3 times 10 plus 4. So that's a decimal representation of any number. You can do this for any other number. So I hope that makes sense. I think it does. So basically the idea is this: you're writing as it as 2000 first, then plus 100 plus 30, and then plus 4. That's how you're writing it out. But this is now a fancy way of writing the same thing. So so we're going to use these ideas to try to get some results on integers that have the same digits or repeated blocks. So an integer, suppose an integer has the same digit a throughout. So for instance, something like this, an integer which has only 2's, it doesn't have any other number, it's the same digit throughout. It can go for as a finite number of places as you wish. So this is the kind of number we are looking at, one that has exactly the same digit repeated. Now, any such number can be written in this form: a multiplied by 10. Ideally, what you have is this. Let's work with a small one. So for instance, if you have 222, you can write this as 2 times 2 multiplied by 111. So now what is in the brackets, you can write it out as 2 times. We'll have 10 squared. So n here is 3. The number of digits is 3. So n minus 1 will be 2. N minus 1 here. And these powers keep reducing until you get to 1 plus 1. So you can write this number 222 in this form. So in general, if you have a number with in which the repeated digit is a, you can always pull a out and multiply it by this sum of powers of 10. Now, if you look at this carefully, you will notice something about this sum. This is a geometric series. You can think of it as geometric series with first term 1 and common ratio 10. And you can get the sum of the first n terms. And so just this part underlined in red can be written as a sum of the first n terms of that geometric series with first term 1 and common ratio 10. Yeah. So this part of underlined can be written more compactly like that, and then multiplied by a. And that's what we have down here. So this number can be compressed, can be represented in this form by just taking advantage of a decimal representation and then using our knowledge of the sum of a geometric series, the partial sum. up to the nth term. I hope that makes sense. If it doesn't, just put on your mic and speak. I do not have a moderator, so I may not be able to check the chat. But if you have a question, just put on your mic and ask. You feel free to interrupt midway. Okay, so the next type of number we shall look at is one where you have blocks of repeated digits. So here we have a block of repeated n repetitions of the 3 digits, right? So for instance, if you have something like 1, 2, 3, repeated again, you keep repeating the same block. So this is 1, 2, 3 repeated twice, 3 times, right? So it's a similar situation we have here. We keep repeating the same block. This is the block ABC, and again ABC, up to the point, the number of times you want to repeat that. So in this case, we assume the number of repetitions will be n. And then if you look at this carefully, it's possible to write this as ABC. Then maybe we can try to work with this number up here first so that you see how this works out. You can pick the first 3 digits, then we'll have 6 zeros for the other remaining places that we have left out. Then the next one will be this. You can put it here, 123. Sorry, I can. So 123. Then you have the zeros. This is 2. Then we have the last bit, which is just the 123. So that's how you can write it out. So, but this first part is 123 multiplied by 10 raised to 6, right? So you will have 10 raised to 6. And then the second part is 123 multiplied by 10 cubed. And then this is just 123 multiplied by 1. So the same number can be written as this, everything multiplied by 123. So if you put it in general terms, this is what it will look like. If there are 3 digits repeated n times, you can write it out like this. But now what you will notice about this is that, again, what you have here is a geometric series. You get its partial sum. These are n partial to the nth term. Now here the common ratio is 10 cubed, 10 raised to 3, and the first term is 1. So the sum of what is just in here, what I have circled, this sum is the same as 10. Just use the sum of a geometric series, and this is what you will get up to the nth term over 999. 999 is the same as 10 raised to 3, the common ratio, minus 1. Then all of this is multiplied by the 3-digit number that is repeated n times. So this number can be written like this. That's all we are trying to do in this. Any questions on this?
No, it's clear to me.
It's clear. Okay. So I will clear all drawings. So this last bullet here is just describing what I was talking about. We are making use of the sum of a geometric progression, the first n terms. So this just illustrates the same thing we were doing. If you have 2,222, then this is what you can write it out like this. So it's 2 repeated 4 times. So n is equal to 4. If you go back to the formula, it will be 10 n minus 1, where n is 4 divided by 9. That's the sum that you're looking for, and then you multiply by the digit that is repeated. The same idea is done here, but this one we've already done an example, so that should be clear. Just to illustrate what is in the results that we have just looked at. So let's see if we can apply this to some questions that would be typical context questions. So the question here says, find the smallest whole number such that its first digit is 4, and the value of the number obtained by moving the digit 4 to the last place is a quarter of the original value. So you have some number whose first digit is 4, so it will have some more digits. We don't know what they are. But now if we rewrite the number so if this is the number A, so the value of the number obtained by moving 4 to the last place. So I pick these digits, I interchange and put 4 at the last place. So if this second number is B, the claim is that this B will be a quarter of the original number. So B should be a quarter of A. So the question is, can we find the smallest whole number that satisfies these conditions? So I hope everyone has had a look at the question sufficiently. So I'll move to the solution now. If you need to look at the question again, you can always ask me to scroll back. So suppose the number we are looking for, we give it this name, we call it y, and we assume it has n plus 1 digits, right? So we know the first digit is 4. So that means the number can be written as 4 times 10 raised to n plus x, where x is made up of n digits. So just to illustrate what's happening here, suppose the number, this is not quite the number, but suppose the number is something like this. Then you can write it as 4. This has n plus 1 digit. So here n is 3. So this one has 3 plus 1 digits. You can write this as 4 times 10 raised to 3. And then you take this number as your x plus 231. So it's the same thing we're doing here. So you see x, in this case, our x is 231. It's a 3-digit number, 1 digit less than the total number of digits in y, the number we are looking for. So I hope that is clear. Now we'll just proceed with the general case now. That example should help to understand. So the original number is this. If you multiply the new number, let me go back to the example. I had 4, 2, 3, 1. So if you change it around, it will be 2, 3, 1, 4. So this is not the answer we are looking for, but if you this is what we are doing. We are moving this first digit to the last one, and then this new number will be a quarter of the original one. So if you multiply the new number, in our case, it's not quite the number we're looking for. If you multiply it by 4, it should be equal to the original number. So the new number will be, remember our x was 231. So if you multiply 231 by 10, you'll get 2310. And then if you add 4, you will get the number you're looking for, which is obtained by moving 4 to the end, right? So 2310, it means you multiply 231 by 10, which is what is happening here, then you add 4. But this new number is supposed to be 4 times. It's a quarter of the original number. So if you multiply it by 4, you should get the original number that you're looking for. So after some simplification and putting terms together, you end up with this. You'll have that this 4 times 10 will be 40x. If you bring this x to the left-hand side, it will be negative. You're left with 39x. And this 4 times 4 can move to the other end, but it becomes negative. I'll put everything in brackets. I've taken some shortcuts. If there's anything you can't follow, just let me know. But it should be easy to see that after some manipulation, this is what you end up with. Now 10 times n minus 4 will be a number which has n minus 1 nines, and the last digit will be 6. An example is if you do 100 minus 4, you will see it become 96. So it was 10 squared. It has only 2 minus 1, which is 1 and 1 9, and the last digit will be 6. If it was 1,000, you will have 1 more 9, and so on. So this is what it looks like. Clear. So this is the answer you get, but it is equal to 39x. So you can multiply both sides by a third, and also multiply this side by a third. And this now reduces to this. You'll have 13x will be equal to 4 times 3, 3, 3. So it will be n minus 1 digits, and the last digit will be 2. And that will be equal to 13 multiplied by x. X is this number here. If you can find x, then we can find y. So now we know the form of this number should be n minus 1 threes and 1 2 at the end. So we can play around for different values of n. We are looking for the smallest possible value. So we could test it for small values of n until we find one that works. So by successively checking for different values of n, starting from 1, 2, and so on, you will find that when n is equal to 5, that is when it works. N is equal to 5 means you'll have 4 threes and 1 2. So if you try this 4 times this is equal to 13x, we should be able to get the value of x that we are looking for. This is the one that will work. The earlier ones will not work. They will not satisfy the conditions we have. So we get x to be this 10,256. Now the number we are looking for should simply be have 4 at the beginning of this x. And that's what we have here. We construct the number by just adding 4 to the beginning of the number x, because that's how we constructed the number. And so that gives us the smallest. We know it is the smallest because we have tested for smaller values of n, and the first value for which it worked was n is equal to 5. It can't work for any smaller value, and any other value after this will give us a big value, a bigger value here. Is that making sense?
Yes.
Good. So let's see if we can do a little more. So here is another question which says, prove that each number in the following sequence is a product of 2 consecutive whole numbers. So this is the sequence. Simply, the first one writes 1 and 2 once. The next one repeats 1 twice, 2 twice. The next one repeats 1 3 times, 2 3 times. So how it works is the next one, next one after this will just have 1 written 4 times, followed by 2 written 4 times, and it keeps growing like that, the sequence. So the claim is that any number in this sequence can be written as a product of 2 consecutive whole numbers. You can quickly see that for 12, this can be written as 3 times 4. So that is true. So what is left is to find, to figure out how to write the general term of this sequence as a product of 2 consecutive whole numbers. So let's look at the solution. So suppose we have, the general form is to have n 1 repeated n times followed by 2 repeated n times. That's what any term of the nth term of this sequence will look like. So we have some things written here. I will just use a small example to illustrate this. So suppose we have 1 repeated 3 times and 2 repeated 3 times as well. Then I can write this as 1, 1, 1 multiplied by 1,000, right? Or 10 raised to 3. So, and then I can add 222. Yeah.
Excuse me, I cannot see what when you start using the note the pen. I cannot see the writing.
Is it that you can't see or it's too small?
I can't see. Sometimes I see, sometimes I can't. Like now, I cannot see.
Is there anyone else who can see?
We can't see the writings.
Okay, that is strange. I can. Let me see. Maybe it's a location. If you notice anything like that, please let me know so that I try to make some changes. Okay, I will try. What if I write on this side? Can you see anything on this side?
Yeah, I can see that.
And on this side, can you see anything I'm writing now?
Before you, yes.
I'm covering the whole screen with red. Can you see the whole screen with red? I'm just scribbling.
Yeah, we can see. We can see.
You can see everything. Or is it just one side of a screen that you can see?
Then margins.
Huh?
On the margins. Me from my end, I'm seeing the writings on the margins.
Okay. Some people can see, others cannot see. So I'll draw a line and you tell me up to what point it has disappeared. Can you still see the line?
No, it has disappeared.
No, I'm drawing a line now. Can you see one?
Yes. Disappear. I can see. Disappeared.
That disappeared?
Yeah, it reached, after reaching the 2/9 disappeared.
Oh, no, I don't know what's going on. Maybe I can try to write on this end, but can you see what everything else on the slide?
Yes.
Okay. Fine, I will try to restrict my writing on this end. So if I have 1, 1, 1, 2, 2, 2, I can write this as 111 times 10 squared, and then plus 2, I think that's it, 222, right? So it's the same thing we have done here, but now you see this one is repeated 3 times. This should be 10-3, not 10 squared, sorry. The reason it should be 10-3 is because I have 3 digits here. I need 3 zeros at the end so that when I add 222, I get this number. So this should be 10 raised to 3, yeah, and not 10 raised to 2. So that's the same idea we are using here. So this is just the how you can write 2 repeated n times. We saw how to do this earlier. So this is a compact form of writing 2 repeated n times. We did that formula earlier. I don't know if I need to go back or you can remember. And then this first part is this is how you write 111 repeated. I mean 1 repeated n times. This number in which 1 is repeated n times. But then we multiply it by 10 raised to n, the same way I multiplied here by 10 raised to 3. So what I pad it with zeros on this other side. Then I can add this n digit number with 2s only. So basically what I'm saying is this: I would have to write all the ones multiplied by 10 raised to n so that I have n zeros on the end here. Then to this n zeros, I can add the number with 2s. That's how I have split it. But now this number with 2's can be written like that. This number with only 1's can be written in this form based on our formulas earlier. But then you have to multiply by 10 raised to n to get all these extra zeros so that you can add the n-digit number, which consists entirely of 2's. Again, I started writing on the left. I don't know if you're seeing anything. But I think it makes sense.
Yes.
Yeah. So we can proceed. So you can simplify this further. After a bit of work, you can move from here to here. You will notice that this number, this 10 raised to n minus 1 is common. It's also here. So when you pull it out, whatever is left in the bracket simplifies to this, right? So you can write, you can rewrite this as 10 raised to n minus 1 over 3, where you pick one of the 3's from this 9. So this number will be an integer because it will be divisible by 9, right? Then this will also be an integer, which is divisible by 3, plus another integer divisible by 3. You can see I've simply rewritten 2 as minus 1 plus 3. It's the same thing. So 2 has just been replaced by negative 1 plus 3. The reason we replace it with negative 1 is we already know there's a term here which is divisible by 3. So if we put it here, it makes our work easier. And if we add 3 again, the whole of this would still be divisible by 3 when we divide by 3. That's the reason we are doing all that. So now this last part, this last part in the product can be simplified to this. You just separate this divided by 3 plus 3 divided by 3, which is 1. And now you realize that this is a product of two consecutive numbers, integers, where if you take a to be 10 raised to n minus 1, then your product will be a multiplied by a plus 1. So we have shown that any number of this form can be written as a product of two consecutive integers, which was the aim of the whole thing. Is that clear?
Yes.
Yeah. So I will move on to the next section. So here we want to focus on perfect squares. So a whole number n is called a perfect square if there's an integer m such that n can be written as m squared. So I think that one is well known. So if I can write some integer as a square of another integer, then I will claim that that integer will be a perfect square. So examples, are like 4. 4 is a perfect square. 9 and so on are examples of, even 1 is a perfect square. So we will list down some basic properties of a perfect square, but we shall not derive them. We'll just use them later to solve some problem. So the unit digit of a perfect square can only be 0, 1, 4, 5, 6, and 9. This is easy to check because if you want to find if P is a unit digit of some number, suppose the number is A and the unit digit is P, right? So then the unit digit of A raised to n will be the same as the unit digit of, suppose P is the ones digit, sorry. P has to be the last digit of this number A, the unit digit of A. So if you want to get the unit digit of A raised to n, it will be exactly the same as the unit digit of P raised to n. We are going to use that here. So if a digit, you can check all the possible units digit. If the units digit is 0, then the units digits of a squared will be 0. If the units digit of a is 1, the units digit of a squared will also be 1. If the units digit of a is 2, the units digits of a squared will also be 2 raised to 4, 2 squared, so which is the same as the units digit of 2 squared, which is 4. And this goes on like this. You test for all the possible cases, and this is all you will get. So a perfect square can only have this as a units digit. No, it cannot have 2. You can't have 2 as a units digit. For a perfect square, you can't have, what else? I think 8. You also can't have 7. I think that should cover all of them. So a perfect square cannot have any of these as the last digit. And I think 3 as well cannot work. So these ones cannot be units digits for a perfect square. So the next thing we look at is that if you have a prime factorization of a natural number in this form, then n is a perfect square if and only if each of these powers is even. So each prime factor occurs with an even power in the factorization, and the number of positive divisors of n is odd also. So this is another thing to note. So there are some techniques for counting the number of divisors of a given number once you know its prime factorization. And it should be, I will skip that. Let's just take this to be true. The number of positive divisors must be odd. It comes from some other technique. I will not go into that for now. Unless someone really wants to know for now. Okay. So the number of tail zeros of a perfect square is always even. So if a perfect square ends in zeros, it must have the number of zeros at the end must be even. It can't have an, for instance, 1,000 cannot be a perfect square. Already we know that, but you can see the number of zeros it has is odd. For it to be a perfect square, you need to have an even number of zeros at the tail end. So you already know that this is 100 squared. So, and as long as a perfect square has zeros at the end, there must be an even number of them. We're still looking at more properties of perfect squares. Also, any perfect squares will either leave remainder 1 or 0 when divided by 3 or 4. So it can't have any other remainders. If it's a perfect square, the remainder must be either 1 or 0 when you divide the perfect square by 3, either 3 or 4. I will avoid the proof for that as well. But this is something now you can apply to a problem. If you know that a number is a perfect square, then if you consider it when divided by 3, there are only 2 possibilities. Either the remainder will be 1 or 0. The same happens when you divide it by 4. The remainder will either be 1 or 0. The remainder cannot be any other number other than 1 or 0 if it is a perfect square. And then when you divide a perfect square by 8, again, these are the only possible remainders you can get. So if you divide a number by 8 and you get a remainder which is neither 0, none of these, 0, 1, or 4, then that cannot be a perfect square. Similarly, if you divide by 3 or 4 and the remainder is neither 1 nor 0, then that number will not be a perfect square. So this can be some quick tests to check if a number is a perfect square. So the next one says an odd perfect square must have an even tens digit. So again, this is something you can use in a problem. So if it's an odd perfect square, then its tens digit must be even. So if you consider an example of an odd perfect square, for instance, 15 squared is 225, I think. I think it is. You can double check that. So anyway, you can see the tens digit is even. If it's an odd perfect square, the tens digit must be even. If it's an odd perfect square, it's an odd number and the tens digit is not even, then that will not be a perfect square. Now, if a tens digit of a perfect square is odd, then the units digit of a perfect square must be 6. So if it is an odd tens digit, then the units digit must be 6. You have examples like 16. So if so the tens digit here is odd. You also have examples like 36. The tens digit is odd, then the units digit must be 6. You can test this for other squares that perfect squares that end with 6. You will see that the tens digit will always be odd. So then the last property that we can consider is that if you have any two perfect squares, then there's no other perfect square in between. So for instance, if I have 2 squared will be 2 squared is 4, then the next perfect square is 3 squared, which is 9. So between 4 and 9, they can't be any other perfect square. From 9, the next one will be 5 squared, which is 25. So between 9 and 25, there can't be any other perfect square. And this goes on in that fashion. So I hope that makes sense. Let's see if we can apply this to a problem. So the problem we are going to apply this to is this one. It says prove that any positive integer greater than or equal to 10 cannot be a perfect square if it consists entirely of the same non-zero digit. So what the claim here is that if you have a number which is bigger than 10, such as 11, it can't be a perfect square, or it must consist of entirely the same digit, as many as you wish, but entirely the same non-zero digit. So numbers like 2, 2. So it doesn't matter how far it goes as long as it's bigger than 10, but it consists entirely of the same digit. Our claim is that this number cannot be a perfect square. Okay, so I can proceed to the solution. So if the repeated digit is an odd number, then the number cannot be a perfect square because an odd perfect square must have an even tens digit. So if all the digits in the repeated digit are odd, then the tens digit will also be odd. So it, based on the properties we saw earlier, for a perfect square, it means this cannot be a perfect square. So that eliminates all the odd numbers. So we have, by the odd numbers would be 1, 3, 5, and 5, 7, and 9. So any number in which every single digit is one of these cannot be a perfect square. So we need to test for the remaining numbers to see if they can work. So if we check for 2 and 8, it cannot be a perfect square, since a perfect square, the last digit must be one of these numbers. So we have eliminated 2 and 8 as well. So 2 and 8. So any number that consists entirely of 2s or consists entirely of 8s cannot be a perfect square, because any perfect square cannot end with a 2, neither can it end with an 8. Now the next one says if the repeated digit is 6, it cannot be a perfect square because the tens digit will not be odd. We said if a tens digit is odd, then the units digit must be a 6. But if it's all 6s, even the last two digits will be 6 and 6, and therefore we'll have a problem here. The tens digit would have to be odd for this last digit to be 6. So we have eliminated 6. So the only one we have not checked is the number which consists entirely of 4s. So let's see how we are going to eliminate that. So let's assume a number consists entirely of 4s and it is a perfect square, in which case you can write it as a square of some integer n. So suppose it's a perfect square. So the idea is to prove this by contradiction to show that this will eventually lead us to an absurdity. So since the square is an even number, the only way that can happen is if n itself is even. So if n is even, it means we can write it as a multiple of 2. So we can write it as 2m. So that means the square of n squared will be the same as 4m squared. And 4m squared will be equal to this. So basically you're saying that this is equal to 4m squared. So now when we write it in terms of m, if you divide both sides by 4, it tells you that m squared will be equal to this number which consists entirely of 1s. You divide both sides by 4. But this is a contradiction because this number cannot be a perfect square. We already checked in the first set that if a repeated digit is odd, then there is no way this number can be a perfect square. And therefore m, this will not work. No such m will exist. So that leads us to a contradiction, and therefore a number that consists entirely of 4s cannot be a perfect square. So we have considered all possible numbers and shown that any number that consists entirely of the same non-zero digit cannot be a perfect square. So are there any questions on that? I want to quickly look at the last one, then we can close the... Is that clear?
I have a question.
Yes.
Can we use the previous method to show that, like the one that we were doing on writing for repeating below, when we have a number of repeated digits, and we write it as in form of as a sum.
So that would work if you know how many digits are in here. We don't know how many digits are here.
Oh, okay.
But there might be a way to play around with it. I don't know. There might be a way of telling how many digits will be here if we know n. So that I don't know that. I have not checked it. It's something you can explore.
Okay, thank you.
Yeah. So here is the next question. It says, suppose we have a 5-digit number in this form. So there are some 2 digits that we don't know. We don't know what they are, x and y. But the rest we know. We know the first, the third, and the last digit. But the second and the fourth digit we don't know. So we label them as x and y. But we know that this is a perfect square. The question says, find the value of 3x plus 7y. So we can solve this. So we will use some estimation. So we need to find the smallest, the largest perfect square that is smaller than, that will have will not have the first digit as 2. So the number we have will start with the digit 2. So we want to find something that is smaller than this, and the 141 I think gives us that. 142 would push us into over 20,000, and that becomes a problem. So this will be smaller than the number we are looking for, our square number. And then the next one is 175 squared, which just takes us over 20,000, and therefore will clearly be bigger than the number we are looking for. We can put that in a better fashion in this inequality. So this is guaranteed. A squared will lie between 141 squared and 175 squared. I hope that is clear. That's the number we are looking for. Now we have some information about a squared. We know the units digit is 1. So if it means that the units digit of a can either be 1 or 9, right? The numbers we are considering will be between 141 and 175. So we need to consider numbers between 141 and 175 with the units digits 1 or 9. And this gives you the full list of the numbers that you can consider. There's no other number that would work. So maybe some of these will work or only one will work. The only way to find out is to check. And if you check one by one, you will see that this works. Because we know what the first digit should be, we know what the third digit should be, and the last digit. We didn't know what the middle one should be. So if you check the others, they will not work. You will only find that only 161 is the one that satisfies all the requirements. So your x will be 5 and y will be 2, but the question is asking us for 3x plus 7y, and that will be 15 plus 14, which is 29. So here we applied estimation to narrow down our options. Once we narrow down our options, we narrow them down further by the knowledge of the fact that the perfect square has a last digit 1, and therefore a itself must have either 1 or 9 as a units digit. And then that means the only numbers we can consider between 141 and 175 are listed here. And then you just, from this point, is just to do by inspection, inspect each of these numbers and check which one fits the conditions given in the question. And turns out 161 is the only one. When you square it, this is what you get. So this is the perfect square that we are looking for. And the value of the second digit and the fourth digit is 5 and 2. If you plug them into this expression, it evaluates to 29. So 29 is the answer that we're looking for. I think that's the last. Any questions on this?
No, it was clear, this one.
It's entirely clear. So thank you very much for joining us for this talk. We should be meeting again in 2 weeks. I haven't set up the topic for 2 weeks, but we will share the topic as soon as it is ready. And we welcome any comments. If you have any comments, any ideas, any remarks, you can share them.